Wire antennas, rhombic antenna, series on antennas and wave propagation, lecture number 4.11. Rhombic antenna is an array antenna consisting of 4 wire segments arranged in the form of a rhombus. It gives unidirectional radiation pattern. It is considered as a traveling wave radiator. In the present session, we consider the structure and design aspects of rhombic antenna along with its radiation features. Before that, V antenna, which is actually half of rhombic antenna, is considered. Its structure and radiation features are described so that understanding of rhombic antenna becomes easy. Let us begin the session with an introduction to V antennas. The basic structure of the antenna is 2 straight wires arranged in the form of English letter V, with feeding at the corner end to each radiator. So V antenna is like this: one wire, another wire, straight wire, arranged in the form of V. Feeding is at this end. Feeding is here as well as here. In case of resonant antenna, 2 types of operations are there for V antennas: resonant operation, non-resonant operation. In case of resonant operation, the other end of individual radiators remain unterminated. If these ends remain unterminated, then it is resonant operation. Whereas when they are terminated on a resistance like this, are made with thick wires, then non-resonant operation results. When working in resonant mode, the antenna is resonant antenna. When working in a non-resonant mode, the antenna is non-resonant antenna. Thick conductors can only minimize reflections over the radiators, giving rise to nearly non-resonant antenna. This fact has to be kept in mind. When conductors are thick, reflections are minimized. Effectively, thick conductors act as conductors terminated on a resistor. To have a pure non-resonant antenna, reflections must be completely avoided, which can be done by matched terminating the radiators. These are radiators. Wires are radiators. If they are not terminated, what happens is the wave which is traveling sees a mismatch here, impedance mismatch at the end, resulting in reflection. Reflected wave also radiates. If the requirement is to have a pure traveling wave radiator or non-resonant radiator, then the radiators, 2 radiators are here, they must be terminated on matched resistance. Some more points regarding V antennas. The termination can be either one of 2 types: ungrounded and grounded. Ungrounded is connecting a matched resistance in between the open ends of the radiators. This is ungrounded. Grounded means connecting a resistance between open end of each radiator and earth. This is one radiator, another radiator. Ungrounded means connecting a resistance like this between open ends. Grounded means the resistance here grounded, another resistance here grounded. In grounded case, the resistance connected to each leg is half of the value of the resistance connected in between the open ends of legs used in ungrounded case. Additionally, the grounded method of termination requires a ground plane. A ground plane is also required in case of grounded method. Another form of V antenna consists of a monopole wire bent at an angle over a ground plane and its image. The included angle and the length of the monopole is varied to tune the antenna. Tuning the antenna means altering its frequency, operating frequency. Here is shown illustrated V antennas. In A is shown resonant V antenna, no termination resistance. In B is shown terminated V antenna and its pattern. Here termination is there, resistance is there. Patterns are also shown. One radiator, another radiator. This radiator gives its pattern. This radiator also gives its own pattern. The pattern of the V antenna is sum of these two patterns which one can find here. Notice it is bidirectional. In case of B, also each individual radiators give rise their own patterns. Together they give rise another pattern which is pattern of the terminated V antenna. Notice it is unidirectional. Some points regarding radiation patterns of V antennas. Pattern of the symmetrical non-resonant V antenna is unidirectional with a main lobe along the axis of the antenna and away from the feed end. It is unidirectional. Non-resonant operation gives rise to unidirectional pattern. It exhibits certain properties depending upon the relation between the included angle. Gamma is included angle between the radiators. Gamma is 2 theta naught, that is the angle between the legs, and the inclination angle beta, that is the angle between the radiator and its main lobe. So the properties exhibited by V antenna depends upon the relation between included angle gamma and inclination angle beta. When the included angle is twice the inclination angle, that is gamma is equal to 2 beta, the pattern of each leg add in the direction of the line bisecting the angle of the antenna forming one major lobe. When the included angle is more than twice the inclination angle, that is gamma more than 2 beta, the main lobe splits into two distinct lobes. When the included angle is less than twice the inclination angle, that is gamma is less than 2 beta, the maximum of the single main lobe tilts upward from the plane of V antenna. This aspect is useful in receiving the signals in ionospheric communications. The pattern of a V antenna formed by slanting monopole at an angle theta naught over a ground plane exhibits following properties. Two important properties are given here. When 2 theta naught is more than 120 degrees, the pattern of the antenna is identical to that of straight dipoles, polarization is primarily vertical. When 2 theta naught is less than 120 degrees, polarization of the radiation along the horizontal direction becomes horizontal. So what is this monopole? Let us suppose here is ground. A V antenna can be designed with a monopole placed at a slanting angle over the ground. This is monopole. This angle is theta naught. Ground creates an image of the monopole. Monopole and its image, mirror image, acts as a full-fledged V antenna. Its radiation properties are described in these 2 points. Now, a few points regarding directivity. In case of symmetrical non-resonant V antenna, maximum directivity usually requires smaller included angle gamma equal to theta 1 plus theta 2 and longer conductor length. For a given leg length L, there is an optimum included angle which leads highest directivity. The optimum included angles, optimum means which is capable of giving maximum directivity. And the corresponding highest directivities for the given leg lengths are available here in a tabular form. Leg length, included angle, directivity. When leg length is 0.5 lambda, included angle is 170 degrees, directivity is 3. Leg length is 1 lambda, gamma is 88 degrees, 4.5 is directivity. When leg length is 1.5 lambda, gamma is 83 degrees, directivity is 6. When it is 2 lambda, gamma is 67 degrees, directivity is 7.5. When leg length is 3 lambda, included angle is 56 degrees, directivity is 10.5. Moving further, we consider now rhombic antenna with a small introduction. Rhombic antenna can be considered as a combination of 2 V antennas, double V type antenna. Rhombic antenna, it was first designed in 1939 by Edmund Bruce and Harold Fries. It is a multi-band broadband array antenna, which may be regarded as double V type antenna. It is array antenna, broadband antenna, multi-band antenna, array antenna. It is in the shape of rhombus. A lot of information is provided in this particular first para. It is an array of traveling wave radiators carrying a non-resonant currents. Thus, it can be considered as a traveling wave or non-resonant antenna. Rhombic antenna is a traveling wave antenna, non-resonant antenna. Therefore, it carries traveling wave currents. It is shape-wise a planar rhombus with 4 legs, each one a non-resonant radiator. Each leg is constructed with 3 wires to counter the current drop. It exhibits good bandwidth 4:1. Here is shown rhombic antenna, structural features and radiation patterns. In A is shown rhombic antenna. 4 legs are here. You can see. Each one with a length of L. This is axis. Terminating resistance is here. Exists here. Angle, the legs make with vertical is indicated as phi's here. In B is a shown pattern. Notice this pattern is when the antenna is in a horizontal plane. Azimuthal pattern at alpha is 10 degrees. Vertical pattern. Alpha is described here. Significant features of radiation pattern. The rhombic antenna can be viewed as an array of 4 long wire antennas, and its pattern can be obtained by pattern multiplication. The resultant radiation pattern is found to be unidirectional, and the main lobe formed is due to the reinforcement of 4 lobes, one from each leg. Radiation obtained is largest along the direction of the axis of the rhombus, which passes along the feed point and termination. So this is rhombus, this is feed point, this is termination, this is axis. There is an upward tilt of the pattern in vertical plane. Directivity ranges from 20 to 90 and the power gain is 15 to 60. Polarization is found linear with the electric vector parallel to the plane of the antenna. Some more points regarding radiation pattern. The antenna is mounted usually over the surface of the ground with its plane parallel to ground, horizontal. It is found that the presence of Earth lifts the direction of maximum radiation upwards in such kind of mounts. A mathematical expression for the pattern can be derived using image theory to account for the presence of Earth. Ground plane creates an image radiator. Now there are 2 radiators, original radiator and image radiator. Image radiator, it alters the radiation pattern of the original radiator. In the present case, the alteration includes lifting up of the direction of maximum radiation in vertical direction. The radiation pattern thus derived gives the pattern in a vertical plane coincident with the rhombic axis as. This is the formula E equal to cos phi sin HR sin alpha sin psi LR whole square by psi. Here HR is 2 pi H lambda, LR is 2 pi L lambda, and psi is 1 minus sin pi cos alpha by 2. LR pertains to length, H pertains to height. Other letters have their usual meanings. Now a few points regarding design aspects of rhombic antennas. 3 types of design methodologies are there for rhombic antennas. They are maximum E design, alignment design, and compromise design. These types are based on the primary criteria to be satisfied in the design. A few points regarding maximum E design. With this approach, maximum electric field E is obtained at the desired angle of elevation. In this approach, the height above the ground at which the antenna should be located is given by this formula. H is equal to lambda by 4 sin alpha in meters, whereas the leg length of the antenna is given by formula L equal to 0.5 lambda by sin square alpha meters. Here the angle alpha is angle the maximum E point of the main lobe makes with the horizontal. For the maximum E condition, the maximum point of the main lobe radiation is not generally aligned with the desired elevation angle alpha. Alignment design. Maximum or peak point of main lobe radiation is aligned with the desired angle of elevation alpha. So basic or fundamental aspects pertaining to alignment design are being mentioned here. For this condition, electric field intensity E at the elevation angle is slightly less than that for the maximum E condition. The height above the ground at which antenna should be placed is given by a formula h equal to lambda by 4 sin alpha meters, whereas the leg length of the antenna is given by formula L equal to 0.37 lambda by sin square alpha meters. Angle alpha in the present design is the angle the maximum point of the main lobe makes with the horizontal. As it can be observed, both designs give same heights but they give different leg lengths. Third one and last design method of rhombic antennas is compromise design. This design methodology gives reduced gain. In case of difficulty in maintaining the required height given by the above designs, the alignment may still be obtained by increasing the leg length. If the height is able to be maintained, but not the leg length, even then alignment may still be obtained by changing the tilt angle phi. If both height and leg length cannot be maintained as given in the above designs, the alignment can still be obtained by varying the tilt angle phi. These are some important points, special points, significant points pertaining to compromise design. Now we move to certain special type of rhombic antennas. Two types of rhombics are used, the re-entrant rhombics and multiple rhombics. What are re-entrant rhombics? What are multiple rhombics? Let us see. Re-entrant rhombics contain an arrangement of transmission lines and matching equipment to transfer the power reaching the terminated end of the rhombic back to the input transmission line. This type of antennas thus has no power loss dissipated in a load resistor and the efficiency is increased, but its disadvantage is the matching and phasing arrangement makes the antenna narrow banded and they require readjustment for large frequency changes. So in a re-entrant rhombics, power loss is prevented. Power loss is eliminated, resulting in high efficiency levels. Multiple rhombics. They have various configurations, all to reduce dissipation losses and to improve the radiation patterns. In one arrangement, two or more identical antennas are connected in tandem so that the output terminals of one connect to the input of the next. The last rhombic gets terminated in resistor. This tandem arrangement results in increased directivity and overall radiation efficiency. In another arrangement to increase the radiation efficiency, a tier of two identical rhombics are installed, one above the other, so as to reduce the high angle radiation lobes and increase the vertical directivity. Now we consider merits and limitations of these antennas. They provide relatively high gain at a relatively moderate cost. They are broadband in nature from the input impedance standpoint, and they are easy for installation and maintenance. These are merits. They exhibit certain limitations too, loss of power in the terminating resistance and consequent reduced efficiency. These are limitations. Relatively large secondary lobes resulting in additional loss and lack of freedom in independently controlling the vertical and horizontal beam widths. These are also limitations pertaining to rhombic antennas. Applications include it is a popular antenna in commercial point-to-point communications and is ideally suited for HF transmission and reception. Now we come to an end of the session. In the present session, we considered V antennas and their radiation patterns at the beginning, and then we moved into rhombic antennas, their radiation patterns, design methodologies, merits, demerits, giving a comprehensive treatment of V antennas and rhombic antennas. Hope this session is useful to you. We meet again in another session soon with a new topic.